Hi, everyone. This is Jason Keith from SB Grid in Boston. Thanks for joining today. Um, Today, we've got Lance Westerhoff joining us from QuantumBio. So Lance is the president and GM at QuantumBio, and today he's going to tell us about XModeScore, protonation, fragment binding, and flip states. So whenever you're ready.
All right. Well, great. Thanks a lot, Jason, for having me. I really appreciate this. This is kind of a really, a neat approach, a neat methodology that really came out of a number of discussions that we had with various pharmaceutical groups and that sort of thing. So I guess just in terms of just a very quick agenda background, we'll talk about a little bit about what level of theory we're using, what the approach is. People that know us and know what we're doing, of course, are they know that we're applying quantum mechanics, semi-empirical quantum mechanics to the process of X-ray refinement and drug discovery in general. And from that, then we've been able to talk about where a proton is. That's a recent publication that I believe you had circulated around, Jason. And then, of course, we have a number of examples and then conclusions. So just as an overview, and when I had done one of these, I guess a year or two ago, I went ahead and had done a lot of the background of what the refinement toolbox is, what we're doing with crystallography. Certainly go back. Everybody's welcome to go back and take a look at that video. But really, the take home here is that if you look at the entire refinement or X-ray crystallography process, a lot of these steps along the way, of course, everybody is well versed with, and are really in many ways outside the realm of what we're doing from a theory perspective. But this aspect right here is where we see a good opportunity, and where we have added a number of methods to improve the underlying structures and what we can do with them. And so, as everybody knows, structural refinement generally or conventionally is broken down to into a restraint library, which generates a set of geometry gradients, and then throw that through a minimizer. And that's pretty similar or the same whether you're talking about Phenix, RefMac, Buster, or pretty much anything works in this sort of a principle. But the issue that we've run into, and this again is well known, that really this SIF approach or this library approach and the underlying functional that's putting all these things together is really missing any sort of understanding of electrostatics, polarization, charge transfer, hydrogen bonding. Basically everything that has to do with a protein binding with a ligand, that's out the window. It's not really included within the methodology. And so what we did a number of years ago, and of course you're welcome to go back and take a look at this paper from 2014, and of course there's a good number of papers that it references beyond that, where we've replaced that conventional approach with at that time it was really a quantum mechanics functional. Now we replaced it with a full QMMM functional, fully automated and everything else that will go through. And now we can capture electrostatics, polarization, charge transfer, hydrogen bonding, and so on and so forth. And therefore executing on that bound conformation. So instead of it being a structure that is based on an unbound conformation, now we have the actual in situ conformation. The nice thing is again, the underlying refinement method, whether again it's Phenix or RefMac or Buster or whatever, it's still based on the same premise that we're generating a set of gradients and then going through that same minimizer. So if we want to think about it kind of schematically, if you will, you can think of, and this again was based on this paper in 2014, where we talked about a region refinement versus a full refinement, where again you had this ligand, you have this main QM region, and then finally a buffer region, and everything beyond that at that time was treated as just conventional stereochemical restraints. And so if you want to think about it from an equation perspective, you'd have a set of gradients. These are your X-ray gradients. So this is, again, it's a refinement, an X-ray refinement. It's not a optimization, as it were. You have the set of gradients from QM, and then finally the set of gradients from the restraints. We've now taken this a little bit further, and we've taken off everything having to do with restraints, and now we have the X-ray, and then followed by the gradients that are associated with QMM. So now you can instead of just being the stereochemical restraints of everything beyond the active site. Now it's actually the entire thing treated as one functional. And this was just recently accepted. We're just waiting for the proof from ACTA D just this year, and it will be under open access. So here's just an example of kind of what we're illustrating. So if you look at the ligand for PHX, it's a distributed in the distributed monolib CIF. Well, there's some errors. There's couple little problems here or there, kind of some odd bond lengths that are weird. There's some funky chemistry going on back here. And we've just gone through, and the only thing we did was we flipped on QM refinement. So we, instead of it doing and using the gradients from this faulty CIF, it goes through and runs it quantum mechanically. And of course, then the strain went from pretty large 550 kcals per mole all the way down to about 16, 17 kcals per mole. Certainly much better. And if you look at then the difference density, again, this is illustrating the fact that this is a refinement, not an optimization. You've got here's the original CIF based PDB, where you had some difference density back here on the tail end. You got some little bit difference density here, a little bit difference density there. Well, all that difference density, not only are you with a better, more or lower strain or lesser strain structure, but you're also having something that fits the density better in this case as well. So we did this in this particular paper. We did this across basically a whole set of structures where it was 50 quasi-randomly chosen structures. We say quasi-randomly because we did pick 10 from really low initial strain, 10 with medium initial strain, and 10 with high strain, and then 10 covalently bound, and then 10 metal-containing structures. And you can see pretty consistently that when we're talking about, in this case, we're talking about improvement as measured by strain. You're talking about a pretty significant improvement of strain across the board while maintaining or improving all of our conventional measures as well, or metrics as well. So once we built that sort of in a toolbox and system, one of the questions that we started to field was, well, boy, if you have better structure, are there other things we can use, or can we get a better understanding of other aspects of the chemistry? And well, it's a good question. And so one of the questions that really came out right off the bat was, boy, can we figure out what protonation state is bound? I thought, well, okay, well, we can do that. But of course, as everybody on this call would know, X-rays don't necessarily see protons. But can we think about other ways of skinning a cat, as it were? So we thought of a little analogy here was, if you think about the planet Neptune. Interestingly enough, it was discovered back in 1846. However, it was actually predicted based upon the perturbations, unexplained perturbations on Uranus a year before. And so we thought, well, boy, can we use the same sort of an approach where we might not be able to, quote unquote, see the protons with the X-rays, but can we see the impact or the effect of the protons on the surrounding heavy atoms and use those to measure whether or not we have the right protonation state? So we happen to use the hardest part of this whole process, of course, actually turned out to, well, can we find some good examples? Neutron diffraction is the go-to, the approach that everybody looks at is saying, okay, experimentally we can show what the protonation state is, but of course everybody knows there's very few neutron diffraction examples, and back then when we started doing this a number of years ago, there was even fewer. Well, and on top of that, oftentimes when we look at an X-ray structure, X-rays structure, you may have crystallized it using different pHs. Of course, pHs are going to affect what your protonation states are. You have all of these little issues that you come about. But we did find this particular set where we had this nice neutron diffraction example and a nice X-ray example done in the same lab, same conditions, the same everything. And so the initial hypotheses is that since we can't conceptualize bonds, we're not conceptualizing bonds as rigid sticks. Can we see a shared proton? Can we see the concept of a shared proton that you may see in this neutron diffraction example? Further, since we're sensitive to these protonation states, can we see whether or not the structure is changing, whether or not we're seeing the right, in this case, arginine 52 out of this example. And then, so therefore, if the model protonation state varies significantly from the real protonation, and when we say real, we're talking about the one that's in the crystal, then the agreement with density should suffer in some way. That would be our hypothesis. So went through, we did at that time we were using, we did a Mo protonate 3D approach for doing protonation. The examples that I'm going to show here in a minute were actually based on we have a built-in protonator now. So if you don't have Mo, I don't believe Mo is available through SG Grid. So if you don't have Mo, you can still use a Mo independent approach for all of this as well. But then we looked at a couple different arginine protonation states. We challenged this with both the Phenix DivCon at the original really high resolution. We also started truncating back the resolutions a little bit to see if we could see, what is there an impact on resolution on the final prediction. And then we finally compared our X-ray results with our neutron diffraction results. And lo and behold, we ran. Here's we didn't run the neutron. We took that from the set that was, or the published structure. Here was the restraint X-ray, and you can see that while the neutron shows a nice shared proton where you have 1.37 angstroms here and 1.21 angstroms here, there is no, obviously in the restraint case, there isn't necessarily a concept of a shared proton. It's basically wherever you put the proton to begin with. If it was on this side, it'd be on here. If it were on that side, it'd be on there. But interestingly, when we ran through our QM refinement, we ended up with pretty much exactly the same, 1.37 and 1.20 instead of 1.21, which was really nice to see. We followed that up with a look at the arginine set. And again, this is a arginine structure where you have this restraint-based protonation. Here's the protonated arginine 52 versus the unprotonated arginine 52. Here's the PM6 at the full 1.3 angstrom, and then finally the PM6 at the 1.8 angstrom, again with those two protonation states. And when you're first looking, you might not see a whole lot of a difference, but if you're really an eagle eye, you'll notice that there's a little bit of a difference density here on this case. But that difference density goes away when you're talking about the unprotonated case. So by looking at difference density, by looking at shared protons, by looking at all these things, we can say, oh yeah, we can measure these things. We can look at these. The QM refinement is good enough to measure whether or not you have the right protonation state. The problem though is, how do you do this? Because obviously looking around at all these little difference densities is going to be really annoying. So we went through and we tried to come up with a more, we'll call it a more automated approach. First, we went through the process of looking at, okay, well, real space correlation coefficient makes sense. Everybody uses it for various approaches. And we thought, well, why don't we look at that? Can we use that to measure whether or not we have the correct protonation state and how well it agrees with density? Well, the problem, though, is that the real space correlation coefficient is pretty strongly correlated with the atomic V factors, or the model precision. And therefore, it's really not a good measure of model accuracy. And so we started looking around, and we went through literature searches, all the standard practices that you're going to do as a research group. And we came across this nice paper by Ian Tickle, where he talked about the z-score, the difference density, and we thought, boy, that kind of sounds like a neat approach. And of course, you go through this, he goes in a lot of detail with the explanation of how it's derived. We rewrote all of that methodology, and it turns out this is an approximate view, but it's basically the z-score, the difference density. And in this case, what he has shown is the ZDD is not correlated with precision, but it's really a model it's a measure of the local model accuracy. And you can do this with a particular atom. You can do this with an entire residue or ligand, or you can do it with really the entire protein if you like. And really, it's important as we go forward here to remember that the lower the score, the better is the key. So from this, though, and we're kind of as people that know us, they know we're a mixed group where we have a lot of strengths in QM and a lot of strengths in crystallography. We thought, well, can we come up with a way to represent what's really going on in the active site, both from a density perspective and from a chemical perspective or a strain perspective. So what we did was we automated a workflow. Again, this is fully automated, so this is out of if you're running this out of SB-Grid, this would be something that you could just run basically just flipping on a switch. Automatically generates the tautomers, the ligand or the active site, goes through and does the region refinement of all those different tautomers or protomers. So you could go through and you'd say, well, okay, I want this set here, and it might have 10 different protonation states or however many it is, and it'll run all those refinements in parallel. It computes the post-refinement strain energy of each tautomer or protomer. And then finally, you also calculate the difference density. So then the XModeScore was basically just corresponds to this equation. So it's very simple from that perspective. So we went through and we did this through, and I'm going to show this as a quote unquote real life example here in just a second. But you've got this human carbonic anhydrase. This one was interestingly enough, if you go back through the history of looking at this particular structure, well, over the years there was a lot of controversy. Now of course everybody knows what the answer is, so it's simple, it's easy. But there was actually a lot of controversy for about 20 years or so what the pertonation states were, right up until there was a neutron diffraction result. And in this case, and again, I'm not sure how easy you can see it, but but you have these three different pertonation states where you have some difference density here. This is after QM refinement, some difference density here, and lo and behold, a little less difference density here with this state. So the question then is, can we quickly and easily pick up this correct form? So the correct form, of course, as I said, it's this one with the least amount of difference density, and that is the one that's also the neutron diffraction. We went through and we did the same scoring that I talked about a minute ago. So this is this XModeScore, which again is the difference density and the strain brought together. And in this case, the higher the score, the better, or the more positive the score, the better. And turns out, again, that same tautomer 3, the one from the previous slide, has the highest score all throughout. So this is at the natural the natural resolution and also all the truncated. Now, of course, I realize that a 2.8 angstrom of a truncated is not the same as necessarily a natural 2.8. But really, what this is showing is that even when you're taking back that density, it is still something that you can use and you can measure, and it still is something that works. We did actually in this paper go through and look at also some natural versions as well, and that's this at least a very similar sort of trend held, where it's, if you're talking about anything between 2 or 2.5 angstroms, it tends to work still pretty very well. And we went on and we did this. We thought, well, okay, the next question is, well, it's great if we can do this on the ligand, but can you also do this on the protein? And sure enough, you can. Where you've got this ASP215, where you're, which one is protonated in which way. You can see these different cases. And again, we have the neutron diffraction study that shows that it's number 1, but we also modeled all these other ones, and sure enough, we could show that the difference, both the difference density and the strain basically worked in cahoots with one another to show that, yes, indeed, structure 1 is the best, all the way back to about 2.5, 2.8 angstrom is where it started to come apart, where it was just very difficult to tell the difference really between any of them. So here's a use case example, and again, this is very similar to if you were to run this today or sometime this week or whatever on SB-Grid. This is how you would run it. So everything up to this point has been shown with using the same sort of workflow or the same process. So if you think about this example is also on our website just under this URL, and you've got this. Basically, we have a wrapper script or a run script that does all of the preparation before you're running Phenix. So instead of we found that one of the things that really helps the user is to understand all those different steps you need to take to prepare a structure, whether that's adding protons, creating CIF files as necessary. All those aspects, they could all be packaged pretty easily into a Perl script that would basically go through and do all that for you. In this case, this is going to take the PDB ID. This is since this is a PDB structure. If this were an in-house structure, instead of using PDB ID, you just use PDB file. Boom, there you go. There's your PDB file. There's your MTZ file, so on and so forth. But we built in the process of if it is a 4-letter code, then it'll go download the files necessary from the PDB and then run XModeScore. We're going to run and generate protonation states using DivCon instead of using Mo or some other methodology. We're going to set aside 20 processors to run this. We're going to create a directory and run within that directory. This is a selection that is basically just the QB Phenix selection language. So we just use their same selection language as you're already aware of in Phenix. We have a chain A, res name, AZM, and then what the res ID is. Now, it should be noted that if you add multiple copies of this, that's fine too. So if you had different versions, and maybe you had 3 or 4 different copies within the structure, that all of that can be run as well. Just drop any one of these points. The pH is important because, of course, as I mentioned at the very beginning, if this needs to be the pH of the crystal. We're modeling, since we're getting against density, we're actually modeling the one that's within that crystal. What protomers we're talking about? So in this case, if you just said 0, 0, 0, it would just be what tautomers are around. But now, if I also wanted to go, well, I'm going to take the negative version as well, so something that's going to be a negatively charged version of the ligand, go to -1. If I wanted everything between -1 and 1, I could do that as well. We're going to use PM6 as our QM method. Amber FF14. Again, this is the built-in version within our Onium or QMMM methodology for everything else. So this will be the method that's applied to the ligand and the immediate active site, and really any other unknown structures that are not understood. So that could be anything like metals or other cofactors or anything else, will automatically be PM6. Everything else, all of the residues outside of the region radius, will just be simply Amber 14. Because we're dependent upon Phenix for this particular methodology, Phenix itself does still do a check to see does everything match up with the CIF file presented. So even though we're not actually using the CIF file gradients, we still have to generate a CIF file. And so we just happen to just say, use elbow, that's fine. You could use pretty much anything. It really doesn't matter. The point is that the CIF that's generated has to match the number of protons that are in the structure. And so this is generated for every one of those. Even though, again, it's to be very clear, it's not actually used during the refinement other than during Phenix's error trap. So if you think about then, if you run this, one last point is this region radius. This is the radius around the ligand. So this would be basically everything within 4 angstroms of the ligand, therefore, i.e. the active site itself. And it is residue extended, so if any atom is hit, it extends it automatically. So this, if you ran this right out of SB Grid using the release version, there's all of our points. And it's downloading the PDB file and the CIF file are automatically from the RCSB, and then protonating the structure just takes a few seconds to protonate it generally, and then it goes through runs using elbow, and then this is where it's kicking off all those jobs in parallel. Because like I said, we said our limit is the number of processors, or in this case, number of threads would be 20. So it will automatically separate that out and say, well, okay, I could run 20, on a single protein, but really the scaling is kind of limited, because if you're looking at just only a few angstroms, you're only talking about really just a few residues. So it's actually faster to say, well, I'll go ahead and run all of these individual jobs in parallel with one another than just running a single job across 20 processors. So it takes care of the math underneath of saying, well, okay, I'll divide that 20 by 3 different calculations among 6. Obviously, then we're just using 18 cores. Generates, runs all the CIFs, runs all the refinements, all of them in parallel. Gives you an understanding of what's going on. So these logs, if you go into all of those individually, those are the Phenix logs. So you can see all the Phenix logs that are being generated. 3 structures still running, 3 structures still running, so on and so forth, and then finally comes down to the completion. So if you notice, this was run a few days ago at 22:14. If I go back, that was the completion time. It started at 21:59. So you're only really talking about a few minutes of a calculation here in order to finally run and come up with all of the different scores. So this was 3 refinements run in parallel with 3 different tautomeric, protomeric states, exactly the same 3 we talked about a few minutes ago. And then you can see here's the strain energies, here's the ZDD, and then the XModeScore for each one of those, all the way down through. And then these, of course, then if you wanted to look at all the PDB files, so on and so forth, you could do that. So what we'll do is we'll go ahead and bring this open. I'll happen to have Mo here in the background open. Again, you could look at this pretty much with any tool that you'd like. I just happen to choose Mo. And again, this one of the neat things about one of the things we added to the underlying script is it will also generate a CIF. In addition to generating PDB files, it'll also generate SDF files. So Mo and most tools can read in an SDF file and just generate all of the information for you. So this very quickly comes into this little Mo database. If you add Maestro, I think Maestro also has a similar database view that you could do. And these were all just done in a CIF sort of format, where you have, again, that same strange energy real space correlation coefficient. As you can see here, the real space correlation coefficient really hasn't changed a whole lot. And that was what I was saying a few minutes ago, where real space correlation coefficient is not a very good measure of agreement with density. But the ZDD, on the other hand, actually shows a pretty significant difference, where this is the, again, lower the better. This is the better one. And then finally, there's your XModeScore. And we can go through and we can look at, and I encourage you to look closely at this structure. As I click through and I go to each one, you can see all the different protonation states are moving around, where you've got actually very little movement in the overall structure, and which makes sense. You're only talking about really adding and changing protonations, but it's just enough with ZDD that we can show whether or not we have the right one, or ZDD and strain brought together, which one's the right one. And you can see, like, for example, this nitrogen moving around as I move through each one of those cases. So obviously this is the winner right here with this lack of a proton. And then we have two other states where here's a proton there without a proton on the backside, and then finally one with a proton here, but also with the backside. And actually, if you notice that, you can see that too, where there was a little bit of a rotation between this one and that one. Even though you're talking about a proton that's back here, that's causing that change. Okay. Go back to presentation mode here. Okay. So what else can we use it for? So we happen to do protomers and tautomers first because protonation states are hard. We thought, well, okay, we'll go ahead and aim high first and see if we can do that. Well, because we were able to do that, what we use this methodology for, and our clients use it for, are not only protomer and tautomer states, but there are also examples and tutorials that show you how to figure out binding modes, which binding mode is the correct one, what your fragment, which fragment is bound within the ligand at what position. We do it for water site locations as well. Flip states, and what that would be is if you from an X-ray perspective, you can't differentiate between carbon, nitrogen, or oxygen. From a quantum perspective, those are very different things. And so if you put the wrong flip state within an active site, we can see pretty quickly that this state or that state is the right one bound within the structure. Rotamer studies, the same concept. It's a very similar type of a problem. And then there's a number of, so basically anytime that you're looking at, if you're ever asking the question, do you have the right species or the right state bound within a density that, might be, whether it's a little disordered or a little problematic, this methodology can help you determine which is the right one, or which is the right ones. Sometimes you end up with a couple different possible states, and these will allow you to see that. Some other features or other aspects that are beyond the scope of the discussion today, but are available within the approach. And again, we've provided this to SB-Grid for all of our academic nonprofit research. And so you're welcome to use this for other types of problems as well. X-ray refinement itself, it's actually a support for 70 different elements. So that's basically going to take care of pretty much everything that you're probably more than likely going to run into, at least on a day-to-day basis in X-ray crystallography. I'm not sure why that's happening there on my screen there. Multiple QM regions. We do support multiple QM regions, so if so you're not held to just one region. If you have, some people, it might be there's a couple different copies of residue or ligands that I mentioned earlier, or maybe you have a ligand over here, a cofactor over there, and an amino acid residue over here that you care about. All of that is all fine and good. We also have as part of the script that we that QB Phenix script, that we also have integrated 3D RISM for water site determination, so we can determine what and if you're not sure what the water site or which sites are actually crystal sites or water sites versus what could just be simply an artifact. We use 3D RISM to figure that out. Very soon we're doing density-driven docking, and that's using a new free energy method that's based on the movable type method. If you want to use the tool for just general structure-based protonation, you can do that. You can, of course, use usual QM, QMM for doing interaction scoring, profiling, optimization, so on and so forth. And certainly, if you have any questions after you've looked at our website, let us know, and we're happy to help. So just a quick rundown of what we talked about. So we can now routinely run this stuff. This is not hard. It's as I showed that AZM example, we were talking about a matter of minutes to be able to run through these type of calculations. We can lead the structure. All of these calculations, they generally lead to structures with lower strain energy. And improved understanding of interactions. Other things we're talking about in terms of the paper, the active paper I mentioned a few minutes ago that just got accepted. In that case, we're talking about clash scores and impact on clash scores and impact on mole probity scores and those sorts of things too. So not only are we seeing improved ligand structure, but you can also see improved protein structure. And finally, in terms of protons themselves, they are significant. We tend to, from a crystallographic perspective, maybe be a little selective with how important we think they are, in part because we generally can't see them. But in reality, they are there. They are impacting the structure, and we can measure their impact on the things around them. Then finally, this advanced, rigorous, when I say advanced in this case, I'm talking about more rigorous refinement. We can really understand much better about what's going on with the structure, and that's certainly from the perspective of publishing a structure. We want to make sure that it's the most accurate it can be, but also if you're trying to look at this from a lead optimization or structure-based drug discovery perspective, these things are important. Certainly become extremely important for understanding what's going on there. And of course, this, as I already mentioned, is available in SB-Grid right now. It's just a plugin for Phenix. If you wanted to use a GUI, that's within Mo, but really for a lot of the stuff, you don't have to. You can just use this as a command line. And in terms of the team, there's obviously the team on our side, which is important. But also, I'd also like to underscore the folks from the Phenix group, especially Nigel. But also Nat and Rolf when he was there, and obviously Paul Adams, but for really providing some initial support and ongoing support, and also including this within including the hooks, if you will, within the Phenix package. And as I've continued to do so, I really appreciate that. In this case, another person I have to also underscore is Ian Tickle. He's been a big help. I guess at the time I think he was at Aztecs, and I guess now he's at Global Phasing. But it's he's been a very good help for us. So thank you for your time, and as I said, certainly drop us an email if you have any questions.
Great. Thank you very much, Lance. I can
No
take some
problem.
questions here. So I do have a question. So a number of groups are using these free energy perturbation calculations for most of what I've seen is GPU based. So is what you have coming CPU, GPU, both, either?
Good question. Yeah, actually, and that was, I guess you could say outside the scope of what I talked about today. But yes, the free energy method is it does not require a GPU. It's extremely fast in the sense that you're running. You can run. It's a very high throughput method, so you can run tens or hundreds or even thousands of compounds an hour, depending upon the size of your cluster. And as I said, it doesn't actually require a GPU, so it doesn't need any of the sort of exotic hardware. I know obviously Jason, you're big into the exotic hardware, but you don't actually need it in this
I
case.
like my exotic hardware, but
You like your exotic hardware, that's right.
it's not always practical.
The GPU, to take the answer a little bit further, the GPU version is ongoing. It is being developed underneath, but with the high throughput, it isn't really required.
Yeah, and I had one follow-up question on that. It's sort of related. Well, it's more about the ZDD actually. Would there be some benefit to just automatically applying that sort of residue specifically through your protein to certain? I'm thinking of amino acids that can have ambiguous side chain conformations. Glutamines, asparagines.
Arginines, yeah.
Yeah, I
Yep.
mean,
Yep.
it might be. If it only takes a handful, it takes 2 or 3 minutes. You could run through a moderately sized protein in a couple hours, right?
That's
You
right.
could,
Yeah, and you could certainly do that. One of the ways that we've added this, and again, I showed kind of the automatic or the automated script-based version. I mean, some folks, what they'll do is some of our clients they actually run this on a like nightly basis through a pipelining process. So for them, that sort of approach works really well. If you have some other scenario, some scenario that we haven't thought of yet, some other scenario that you would like to measure or approach, and the one you just described would be a great example. Where you want to go through and you want to look at all the different possible main rotamer states of a protein or whatever. What you can do is you actually just load up a directory. There's an example like this for I guess it's for a docking study, where you can load up a directory full of all of your different states, and it will just simply go through automatically through all those different structures and calculate your ZDD based upon that. And so, yes, certainly you could do something like that. It'd take a little bit more scripting to do, but you could do that.
Lance, thank you very much.
Certainly, thank you, and certainly, pass along any questions or anything that people have. We're happy to help.
And for anyone who wants to give this a shot, I think 7.1.1 is on your machines now. 7.5 is on its way in this month's update, which should be out tonight or tomorrow. And if you want an advanced version, just drop me an email and I'll send it your way.
Sounds good.
Great.
All right, great. Thanks a lot.